There's a world that exists right under our noses. A world that's not just small, but fundamentally different. It's a place of pure potential, this shimmering, uncertain reality that, believe it or not, governs everything we see and touch. Today, we're going to talk about how scientists are learning not just to look at this world, but to actually take control of it.
So let's just start with this question. What if you could actually see an electron move? I mean, really watch it. It sounds simple enough, right? But the journey an electron takes inside an atom is one of the fastest things that happens anywhere in the universe. Trying to capture that, it'd be like trying to photograph a single bolt of lightning with a camera from the 1800s. The event is it's over before you can even blink. And the result you get isn't just a blurry photo, it's a problem baked into the fabric of reality.
Yeah, that blurriness, it's not just a limitation of our gear. It's a core feature of how our universe works. When you get down to the quantum level, reality itself is kind of jittery and uncertain. So before we can even think about controlling it, we've got to understand the rules of the game. And rule number one is the big one, the Heisenberg uncertainty principle. Now, what's so important to get here is that this isn't about us having clumsy measurement tools. It's a fundamental trade-off. Think about it like this. You're trying to find a tiny, super fast particle in a dark room. To see it, you've got to shine a light on it, right? But the very act of a single photon of light smacking into that particle sends it careening off in a new direction. So the more precisely you pinpoint where it is, the more you've messed up where it's going.
And this is the part that just blows my mind. This quote nails it. This isn't a problem we can just solve by building a better microscope. It's a hard and fast rule of reality itself. It's almost like a cosmic speed limit on what we're allowed to know. For decades, this principle, it really seemed like a total dead end, an absolute barrier. But what if you could bend the rules? What if, instead of trying to break this law of physics, scientists developed some incredibly clever tools made of pure light, that actually work with this uncertainty? Well, that's exactly what they did, and it's given us a completely new way to see the quantum world. Okay, so we're going to look at two of these revolutionary tools. On one side, you've got something called squeezed light. This stuff is designed to quiet down that inherent fuzziness of the quantum world, the noise, so we can make measurements with almost impossible precision. And on the other side, we have attosecond pulses. Think of these as the universe's fastest camera shutter. So fast they can literally freeze the motion of an electron in its tracks. Two totally different problems, two absolutely brilliant solutions. All right, let's start with squeezed light. How in the world do you measure something more precisely than reality itself seems to allow? Well, here's the trick. You don't actually get rid of the uncertainty, you just move it around. And honestly, the best way to think about this is the water balloon analogy. Picture quantum uncertainty as a water balloon. You can't make the water inside just disappear, right? But you can squeeze the balloon in the middle. Where you squeeze, it gets thinner. That's you reducing the uncertainty in one particular measurement you care about. But what happens? The water has to go somewhere, so the ends of the balloon bulge out. That's the uncertainty in another property increasing. You're basically just shoving the uncertainty over to a place where it doesn't mess up your experiment. It's so clever. So how do they actually do it? Well, to put it simply, you take a normal laser beam, which has a bit of natural quantum randomness to it, and you fire it into this special crystal. And this crystal, it kind of acts like a photon matchmaker. When two photons happen to show up at the exact same time, it smashes them together into one single photon with more energy. By doing this over and over, the stream of photons that makes it out the other side is way more orderly, way more predictable. It's literally quieter. Now, to make this whole process even more powerful, scientists use something called an optical cavity. You can basically picture it as a hall of mirrors that traps the light, bouncing it back and forth through that special crystal thousands of times. Every single pass enhances that squeezing effect, making the light quieter and quieter and quieter. And the results? They're just staggering. I mean, look at this chart. That first bar is the standard quantum limit. That's the baseline level of noise the universe says you have to deal with. But with squeezed light, labs have now achieved a noise reduction of up to 13 decibels. Now, that might not sound like a lot, but in this world, that is a massive leap in precision. It lets us push our measurements way beyond what we ever thought was possible. Okay, so why does this all matter? This isn't just some cool lab trick. Squeezed light is already being used right now to make gravitational wave detectors like LIGO way more sensitive. It's helping us hear the incredibly faint chirps of black holes colliding billions of light years away. It's also letting us build new kinds of sensors that can watch what's happening inside a living cell without destroying it. This is a tool that is fundamentally changing the game. Okay, so that's how we quiet the quantum world. But what about actually watching it move? This is where we pivot to our second amazing tool, attosecond pulses. We're going from listening to the universe more clearly to filming it in the most extreme slow motion you can possibly imagine. Just take a second and look at that number. 10 to the minus 18th power. That is an attosecond. To give you some perspective, there are more attoseconds in a single second than there have been seconds in the entire 13.8 billion year history of the universe. It's an almost incomprehensibly short amount of time. And it just so happens to be the natural timescale for an electron. And this is what one of those pulses of light actually looks like. It's this incredibly short, incredibly intense burst. This is it. This is the shutter speed for our quantum camera. It's so ridiculously fast that it can grab a snapshot of where an electron is inside a molecule before that electron has had a chance to go anywhere else. So what do? You fire a whole sequence of these pulses, one after the other. And by stringing those snapshots together, you can create, for all intents and purposes, a stop-motion movie of chemistry as it's happening. We can now literally watch a chemical bond break. We can see a molecule twist and fold into a new shape, frame by painstaking frame. And check this out. This is not a simulation or an artist's impression. This is actual data from a real experiment. What you're looking at is a molecular movie of a molecule getting blasted apart by light. You can see its fragments being tracked over hundreds of femtoseconds. And remember, a femtosecond is 1,000 attoseconds. We're witnessing the basic machinery of chemistry as it happens. It's unbelievable. And that really gets to the heart of why this is such a big deal. You know, this quote from a JILA report says it all. The grand challenge, the ultimate goal, is to see the quantum world operate on its own terms, at its own natural speed. And with these tools, we can finally do it. So we've got tools to quiet the quantum world down, and we've got tools to film it. This brings us to the really exciting part. What's next? What can we start to build now that we have this incredible, unprecedented level of control? You see, we're living through a massive shift in science. The first quantum revolution, the one that gave us things like lasers and computer chips, that was all about just trying to understand the bizarre rules of the quantum realm. But this second quantum revolution, the one that's happening right now, is about becoming masters of that realm. It's about learning how to manipulate and control quantum systems to actually do what we want them to do. And the possibilities from here are just out there. This level of control is laying the absolute essential groundwork for building truly powerful quantum computers. It's letting us design brand new materials, atom by atom, with properties we've only ever dreamed of. And it's giving us the ability to test the fundamental laws of physics with so much precision that we might discover new forces of nature or find cracks in our current understanding of the universe. And what's really cool is how all of this stuff is connected. These tools, the squeezed light, the attosecond pulses, and a bunch of others, they aren't just isolated tricks. They form the bedrock of this entire field called atomic, molecular, and optical science, or AMO for short. It's like these rings here. Each tool is linked to the others in such a way that the whole thing is way, way more powerful than any one piece by itself. A breakthrough in one area immediately opens up new possibilities in all the others. So we end up right back where we started, but now with a totally new perspective. We are no longer just passive observers looking at this blurry, jittery quantum universe. We're becoming its architects. The question isn't if we can control the quantum world anymore. The question is, what are we going to build with that power?